Our next speaker is Matthew Kolosick, and we will actually hear about constant time in two talks in this session. But for this one, it's about robust constant time. So then we will ask the following: what is not robust about the definition? I believe that you are on the industry job market.
Yes.
So the floor is yours.
Hello, I'm Matthew. I just graduated from UC San Diego, and this is my work on robust constant time cryptography in collaboration with a number of co-authors. So I'll give you the introduction to constant time cryptography. So as we all know, cryptographic code underlies pretty much everything about security in anything internet or distributed at all. And broadly, we can think of cryptographic code as we have some like message encryption and there's some secret key. But crucially, when this code is actually running, we have it running on actual software and hardware. So we want to make sure attackers can't steal our secret keys, even if the cryptographic code itself works. And to this end, we need to worry about things called side channel attacks. So this is, for instance, if this encryption function for two different keys ran in different amounts of time, then an attacker who can measure how long the function takes to run can figure out which key was input. And the security property related to this is what's called constant time. So if the encryption function worked like this, then it would not be constant time. However, if for all inputs, all secret inputs, the runtime or sort of these side channels were the same, then this code would be constant time. And a really nice thing about constant time is it gets us a bunch of design principles. So this is a very simplified version of some actual code from the libsodium library. And constant time has these rules of thumb that we can follow. So you can do things like don't branch on secrets, don't use secrets as pointers, and only use constant time operations. And together, this ensures that your code is constant time. And so this code is constant time. It won't leak secrets through side channels. But I want to draw your attention to this line here, this mem0, which appears in the actual libsodium. And it has nothing to do with constant time. And before we get to this, I want to remind you of sort of a lesson, a mantra in cryptographic code, which is don't roll your own crypto. And we see throughout history that when people try to sort of write their own cryptographic algorithms and protocols, it's very difficult and you tend to get it wrong. And what this leads to is that the reality of cryptographic code is that it's written as libraries by sort of cryptographic developers and then used by the rest of us. So that is, cryptographic code doesn't just look like this nice little encryption function. It is a function being used in an application by those of us who do not write cryptographic code. And this means that constant time, the model of classic constant time, is these keys are just treated as arguments to a cryptographic function. But the reality is these keys live somewhere in the memory of the application itself. And then security of the whole system depends on application behavior too. So a buffer overflow within your application that can access those keys is still access to those keys even outside of timing behavior. And the thing is, cryptographic developers are thinking about this. So that line, that memory zeroing from libsodium is making sure that a stack overflow doesn't leak this secret information value. And in particular, libsodium uses throughout the library a bunch of secure memory clearing for these temporary secrets. Further, they provide a bunch of guarded heap allocation APIs to ensure that these secrets can be protected at rest. So you might say, just write your applications in Rust. This means that we don't have to worry about buffer overflows and things. However, in the modern era, we also have to worry about things like Spectre and speculative execution, which sort of break all of our assumptions of memory safety, and also, to the side, ruin many of our rules of thumb about building constant time cryptographic libraries. So with classic constant time, we have a security property that captures there's no side channels in the crypto functions, but this doesn't capture the larger picture. So we propose instead that the security property that you really care about is what we call robust constant time. That is, the library must be secure when linked against an entire application. And by switching to this setting, this lets us model different attackers. So are there read vulnerabilities? Do you care about Spectre? Is there a concurrent thread who might be observing what's happening? And by doing this, we can sort of capture which things a cryptographic library should be concerned about. And further, we use this to design a compiler that lets us sort of pull these security concerns out of the library itself and automatically protect cryptographic libraries. So in the rest of this talk, I'm going to talk about how we actually define robust constant time, look at how we model speculative execution and constant time for this project, and then finally talk about our robust constant time compiler. So robust constant time. So we've got two parts. We've got libraries and applications that need to fit together. So to model libraries, we just say, first we start with an API, so the set of functions that the library provides, and a set of secret contexts. So these are the keys and secret information that you want to keep secure. Libraries then implement these APIs and can use these secrets and contexts. On the other hand, the application simply uses functions from this library API. And in our model, we use a block-based memory model, which gives us a way to model sort of overflows as access beyond the edge of the block. Further, we build a model of memory protection instructions, which we're going to use to build secure compilers. To define robust constant time, we then start with a library that we want to ensure is secure. We consider all applications and pairs of keys, so we must consider any application this library can be plugged into. And then the whole program plugging in must have the same traces, so must have constant time behavior. If so, this library is robustly constant time. But I want to focus in on this for all applications, because the reality is cryptographic libraries are used in many different application contexts, C applications, Rust applications, etc. And this means that you might have different sets of assumptions about what's going on in the application. Are there read gadgets? Are there write gadgets? Are we on a speculative processor? Is there a concurrent thread? So we don't want this sort of broad for all applications, and instead want to model different attackers as a restricted set of contexts that we care about. And in particular, we're going to restrict based on assumptions about how the application behaves, as we talked about earlier. And in particular, these are going to capture actions that the application can or cannot do. And in the paper, we instantiate for several particular application assumptions, including memory unsafe attackers, which can read or write out of bounds and are essentially unbounded attackers, having read gadgets, which can only read out of bounds but can't take these sort of more active attacks, and then memory safe attackers. So these are applications like Rust. We further model both speculative execution and concurrent observers as sort of a separate class of attacker models that are going to be related to having read gadgets. Formally, these are properties about the application, but the problem when modeling this is that applications have a hole where the library goes, so we can't actually run these. So our idea then is to capture assumptions in the application as something that must hold for all well-behaved libraries. That is, we can separate our trace into a back and forth between application and library, and for instance, memory safety, that is that there's no out-of-bounds behavior in the application. We require that there's no out-of-bounds behavior, but then we may assume that the library behaves properly and then that our trace continues accordingly. Capturing robust constant time for memory safe attackers then is simply for all applications that are memory safe for all well-behaved libraries. We have this constant time property, and our other properties defined similarly. Speculative execution, on the other hand, requires a little bit more complicated model. And for those who don't know, speculative execution is sort of a more recent attack vector where modern processors in running speculate on which branch to take. So for instance, if we have this bounds buffer check, this is generally going to be the case that most indices that are checked are below the length of the buffer, and so this code generally takes the if branch. However, if an attacker can influence, like, okay, we're going to pass something outside the bounds of the buffer, the processor will speculatively start executing code. It's like, okay, we're typically taking the if branch, so let's just start running that. And the problem is, eventually the processor will realize that the guess was wrong and roll it back, but traces of this path, the sort of erroneous execution where we read out of bounds, still remain. And the problem with this is that it breaks all of our assumptions. We can't necessarily rely on applications being memory safe anymore because speculatively they probably aren't. And to deal with this, we captured a notion of speculative robust constant time by defining a high-level speculative semantics for our language and capture sort of a broad essence of Spectre and speculative execution with a speculator. So this is going to let us capture different versions of Spectre. So for instance, the classic Spectre v1 attack where we do this bounds buffer bypass, or bounds check bypass, what's going to happen is the speculative model lets you sort of guess the speculator, the attacker, guess the result of an expression. So here, you would guess false, or sorry, guess true for this, and then continue running, even if the index is out of bounds. Versus for Spectre v4, store to low forwarding, we can capture with the exact same mechanism, where it is simply guessing the prior load value and continuing as though a previous write had not occurred, and then continuing forward. Speculative robust constant time is then just robust constant time in this attacker model. So lastly, we use these ideas to build a robust constant time compiler. And so this is coming from, there's lots of different attackers, and this leads to a lot of different protections. Unfortunately, there's no one fast solution. And what we found is that current libraries are making basically one choice of an attacker that they're concerned about. So libsodium has these memory zeros, but there's a sort of closed issue where someone points out, oh, this is missing a memory barrier, a fence, that would be needed to make this speculatively safe. And they go like, okay, Sure, that's true. But if we did that, then we would protect against Spectre, but many people don't care about that, and it would slow everything down. So coming from the PL world, we know that we have a solution to this, which is like, let's pull this choice out of the code, and instead build a compiler where you get to parameterize what your attacker model is. And we're going to build, and we build this on LLVM and Clang. This way you can choose what you're protecting against based on where you're deploying. So to sort of high level go over this, I'm going to talk about our read-only attacker mode first. And so the sort of high level of how this works is we're going to start by allocating all of the secrets in a protected memory region. Then when we're going to be actually running the cryptographic code, we're going to switch to a protected stack so that we only allow access to protected memory while we're running within the library. Then return, when you return to the application itself, we're going to switch back to the program stack. But this ensures that all secrets are kept basically only existing while you are running within the library. And this is separate from constant time itself, so the constant time of the library is sort of orthogonal to our protections. In speculative mode is very similar. We just also must do things like fencing to prevent speculation crossing these boundaries. And in this case, you must bring your own speculative constant time. In the paper, we show how to prove a Robocop secure by building a logical relation that semantically interprets traces and proving that each of our parameterized compilers gives the respective robust constant time property. Lastly, so we implement this compiler in LLVM and Clang, and we measure using the SuperCop benchmark suite what the overhead is on approximately 500 algorithms. And we find that the median overhead for both our read-only and speculative protections is about 0.13%, so very low cost for these algorithms, and 75% of our overheads are below 2% for the read-only protections and 4% for speculative, where the fencing sometimes causes a slightly higher slowdown. So thank you. That's our work on robust constant time cryptography, and you can find this paper at the link below.
Any question?
Hello. Yes, thanks a lot for interesting talks. So, but I have one aspect that I have to argue with you is that Spectre being considered to be the recent or contemporary, because I'm from the security domain, and that this has been very popular for the last decade, and then most of those were addressed, or unnecessarily, we don't necessarily agree upon this. This will eventually resolved by the hardware vendors, right?
Yes.
So, so my question here is that outside of this kind of like ongoing issues or past issue, can you give us more generic threat model where your research can find a context?
Yeah, so I think that I agree that like ideally we fix these like speculative attacks in hardware, and there's been lots of pushes. However, there is still significant amounts of like deployed hardware that cannot be fixed. People are continuing to find sort of new side channel and speculative exploits. So I think that like software techniques for ensuring protection against these are still like useful and important until these are sort of like, we figure out as a like overall community how to like permanently fix these speculative execution. But I think a key here in this work is exactly also in line with this, which is that like not everyone should care about like doing these speculative executions. We don't want to bake them into every protection, which is why we parameterize by different attackers, so that you're like, okay, I don't actually care. Like I'm on hardware that deals with Spectre appropriately. I think that like the people that might be exploiting this aren't going to be going to that level. And so we want to ensure that our security sort of takes into account the different possibilities for what you might be concerned about, and that you can sort of operate faster in cases where you do not care about these things.
Maybe I have a question myself related. So in your speculative model, you consider branch as a source of speculations. There are a lot of other works that try to expand that speculation mode to more. For example, when you have a return stack buffer, you might not just speculate on branches, but on any return of function or call of functions. Could you extend reasoning about robust constant time in those kind of scenario as well?
Yes. And so we specifically model speculation at like a higher, so like I showed the example with branches, but it's really just the speculative model is that a speculator can just guess there's like a microarchitectural state abstractly, and then the speculation oracle can guess the outcome of any expression and start sort of running as if that expression had that outcome before checking. So that can be things like what the return of a read is, what a memory address is, branches, the target of a call, and we talk about all these in the paper. So yes, it's a very broad speculation model.
Okay.
Yes. So when you motivate your work, you also mentioned there might be other threads running. So is there some idea related to concurrency that you are considering?
Yeah, so I didn't talk about this in the talk, but in the paper. And so there, when you're worried about sort of a concurrent thread, a number of cryptographic algorithms will sort of do the intermediate work within sort of an output buffer. So you might use the ciphertext output buffer to do the intermediate rounds as well. So you don't have to reallocate space. And when you're operating in a concurrent threat model, you have to, if that is in unprotected memory, then that is, an attacker can observe the intermediate values there. So what we have to do there is actually allocate all of those, a copy of all those buffers internally and copy in and copy back out to ensure protections.
So what about operating system level concurrency? I mean, do you have to build a secure enclave, try to isolate?
So here, the memory protection we use is through Intel's memory protection keys, and so that protects from concurrent. So that is a thread local memory protection, so the access is only available in the current thread. So that handles that.
Okay. Any other question? No? Well, thanks to the speaker.